Welcome to Space News from the Electric Universe, brought to you by the Thunderbolts Project at thunderbolts.info. In part one of this two-part presentation, Dr. Raymond Gallucci began his independent mathematical analysis of cosmological alternatives to the standard interpretations of cosmic redshift. For many decades, astronomers have believed that cosmological redshift indicates the, quote, stretching of light in an expanding universe. The higher an object's redshift, the farther away it is from our perspective on Earth. However, as we've reported exhaustively on this series, an imposing body of scientific research contradicts that perspective. Today, Dr. Gallucci concludes his analysis on the mathematical plausibility of the respective alternative redshift explanations by scientists Halton Arp and C.C.
Now let me switch over to the quantization concept, and I'll now read from quotations from Halton Arp's talk given to the Kronia group at the conference in Portland in Oregon 2000. He was talking about his theory on intrinsic redshift. In the early 1950s, they saw thin connections between galaxies and radio lobes, going from the central galaxy out to the radio lobes on either side. This material is actually being ejected. That's about the only way you could get this configuration. If the galaxy is going to eject something, it's going to eject along the paths of least resistance, which is out the poles of the galaxy. You have this nice relationship that, as the quasars proceed out as time goes past, they age and drop in preferred quantized redshifts. What I, Halton Arp, have interpreted this to mean is that these quasars move out, evolving to low redshift. And if you look at the various videos or some of the websites or even the books that Halton Arp has published, he has some very nice pictures that show galaxies, a parent galaxy with a series of smaller galaxies at various distances from the galaxy with these quantized redshifts. So if we look at the regression fits that I had back on slide 10, again, there were 5 regression fits, of which 3 I selected as being possible contenders for calculation for quantization. What I have here, I have the 5 observed redshift peaks, their time increments. Again, the redshift drops as the time or the distance increases, so you'll see that the time increments go from 5 down to 1, while the z peaks go from 0.3 up to 1.96. I then took the 3 best regression fits. The first was a function of the square root of the mass ratio. Again, the mass of the quasar, or QSO, to the mass of the sun. The second fit was based on the natural log of the ratio, and the third was based on the ratio to the 2/3 power. And I calculated the mass ratios that would come from these formulas, and their average is shown in the rightmost column. So those are the values of the ratio of the QSO mass ratio for the various z peaks. And the text there reads, from the 3 best regression fits, estimate the QSO mass at each of the main 5 redshift peaks. If there is a quantization phenomena as the QSO is ejected and travels outward, with redshift decreasing in specific increments, these are increments of time or distance, we expect some relationship between redshift and therefore mass of the QSO with time and or distance, with time or distance increment 1 being associated with the newly ejected QSO. That's shown as time increment 1. It has a redshift of 1.96, a scaled mass ratio of about 2 times 10 to the 9th. It's the largest redshift, and it's also the largest mass. And increment 5 associated with the oldest QSO. That's shown as in the first row. That's the redshift of 0.3, the scaled mass of 1.65 times 10 to the 8th, about a factor of 10 lower. So again, Arp's theory is that as the QSOs are ejected, they travel outward from the parent galaxy, and their redshifts drop with time, which is the same as with distance, as their mass decreases. Now again, going back to the previous slide, I'm going to do another regression using the average mass ratio in the rightmost column at the various time increments, 5, 4, 3, 2, 1. which are analogous to distance increments. And you can see the results there. On the graph, we have the mass as it's scaled to the mass of the sun versus time or distance increment. And again, I had 5 regression fits. The exponential in purple fits the data best, passing through all the quantized values. The natural log in blue is nearly as good. The inverse time, shown in green, is slightly weaker, but it's still acceptable. And if you look at these, you'll see that all 3 of these, the ones highlighted in yellow, stay above 0 through the 5th increment. The other 2 that are still decent fits do that hit down to 0 around 5, so I didn't work with those any further. The question asked is, do any of these in yellow highlight suggest a quantization mechanism? Again, let's return to Halton Arp's talk at the Chronia Conference Group in Portland, and I'll quote from him again. Here he's now talking about particle mass being variable with time. And to quote Halton, Einstein's solution made in 1922 made an approximation which I, Halton Arp, think was wrong. The particle masses were constant everywhere in the universe. That was the approximation by Einstein. With this approximation, they got the Big Bang solution, and they predict expanding coordinates, singularities as time equals 0, and this demands that all the redshifts are velocities of recession. Jack Narlikar and Fred Hoyle did not assume that particle masses were constant in time, and they got a very simple solution that the masses varied with the time squared. That is, as time went on, they communicated with more and more of the universe and their mass grew. This is a Machian theory. If the electron mass, when it makes its transition in the atom and emits the proton, is small, the photon is weak and it's redshifted. As the electron grows in mass, the photon which is emitted is stronger and it drops in redshift. So this is a perfect explanation for what we've been seeing, that younger objects are highly redshifted, and the sacred Hubble constant is just the inverse age of our galaxy. Continuing with Halton Arp's talk at that conference, if you start in the galaxy nucleus, you get a high density in the center of this active nucleus, this mysterious engine where the stuff is created. The new particles are in that environment, and they're gaining mass from their environment very rapidly. When they step out of the nucleus, they go into a different, much lower density environment, into the bulge of the galaxy, and then if they come out in the plane of the galaxy or along the axis, they drop here into the local group. These are enormous drops in density. And finally, when they drop out of the local group of galaxies, they take another step down into the local supercluster of galaxies, and out the local supercluster, they take yet another step down. These particles will be gaining mass very rapidly, and the redshift will be dropping very rapidly, and then it finally levels off. And there goes another step in the drop. And there are just about 6 drops, and there are 6 major quantization levels. And he quotes the values of 1.96, 1.41, 0.96, 0.6, 0.3, and the one that was postulated at very low 0.061. And the following slide, this is taken again from Halton Arp's talk at the Chronia Group. He presented a series of slides that show these drops in density, and I made a composite schematic from his presentation. And there's incremental increases in particle mass and corresponding quantized drops in redshift. If we start from 0, which is at the top, that shows the galactic nucleus, and the leftmost axis there shows drops in density, while the left axis, the vertical axis, and the y-axis, the x-axis is time distance as the QSO moves outward. So we start from 0, which is the galactic nucleus, then proceed to the first step, which is the drop to the galactic bulge, which is step 1. Following that, we go to the galactic plane or axial ejection, which is shown as step 2. That then proceeds to the local galactic group, which is step 3. Next goes to the galactic supercluster, which is step 4. And finally, then there's a step 5, which is postulate. He does not specify what that is, but again, the key here is that Halton Arp sees these stepwise incremental increases in particle mass corresponding to the quantized drops in redshift. So this is his explanation for the quantization of redshift. Now I'd like to talk a little bit about the theory of C.C. Su, from whom I used the redshift data. This is from an article taken from the arXiv website in physics in 2006. According to Su, is the following. According to the ejection model, quasars are formed from the gas of atoms, plasma, and dust ejected from the parent active galaxy. Suppose that the material of the gas cloud together forms a local ether. The gravitational potential on the surface of the quasar is extraordinarily strong. The wide variation in redshift can be ascribed to a variation in density and size of the gas cloud, which can be due to the strength of the initial ejection from the parent galaxy, the speed at which the cloud moves away, to the gas expansion, to the fragmentation of gas clouds, and to star formation. So he has multiple explanations for the wide variation in redshift. Due to the non-uniformity in particle velocity and density, or to some internal disturbance, the quasar may break into pieces of identical or similar sizes. Suppose the fragments are also spherical and the density remains unchanged. Thereby, their radius is shorter than the previous one by a factor of 2 to the minus 1/3 power, and the gravitational potential on the surface of either fragment will decrease by a factor of 2 to the minus 2/3 power. And after the nth splitting in half, the gravitational-induced intrinsic redshift is given by the formula shown there. 1 plus z to the n equals the square root of those terms there. Continuing with gravity-induced quantization from C.C. Su, one of the terms inside the square root on the previous formula, the 1 plus z0 squared minus 1, denotes 2 times the normalized gravitational potential, corresponding to the zeroth redshift 0, z sub 0. For the cases of very high redshift, this can be approximated as 1 plus z to the n equal to 1.26 to the minus n times 1 plus z sub 0. By adopting the preferred redshift value of 1.956 as the zeroth redshift once again, this formula leads to the prediction that the preferred intrinsic redshifts are a series starting at z equal to 6.08, and shown there are the series down to 0.06 with n equal minus 4, ranging from minus 4 to 9 by integers. And the ones highlighted in red are the ones that have been observed. And a redshift distribution, you notice that the 0.6 isn't shown there, but what C.C. Su observes is that a redshift distribution around 0.6 may actually be a merger of two close distributions around 0.71 and 0.49, which are two that he predicts, and that just happens to be the average of the two, 0.6. So he does get the 6 key redshift peaks from his formula. Low redshift peaks are expected to be smeared, since other affecting factors of uneven splitting, gas expansion, and star formation will accumulate with time. Now, my observation is that, unlike Arp's theory, Su's does not postulate the series of quantized redshifts represent QSO evolution with time and/or distance, although he does agree that QSOs are formed by ejection from a parent galaxy. His quantizations are static for each QSO and dependent upon various initial conditions and interactions until the QSO stabilizes and exhibits one of the characteristic preferred redshift values. So whereas Arp believes that QSOs are rejected and they evolve with time as they move outward from the parent galaxy and their redshifts drop in quantized amounts with variable particle mass, Su's belief is that they're all ejected at the given redshifts that are already quantized due to other factors. It's not a case of each QSO going through an evolution and a change in its quantization of redshift. Now I'm going to offer some speculation on my part. From Halton Arp's theories, the QSO quantized redshift varies with QSO distance or time from the parent galaxy, which could be either or both a time or distance phenomenon. QSOs are ejected with high redshift, which seems to correlate well with high mass, therefore high density, providing the emitting nucleus remains relatively constant in size. Arp bases the observed quantization on variable particle mass, which increases with time and correspondingly with distance as the particles evolve and travel outward from higher to lower density regions in a piecewise, not continuous manner. If you accept Arp's variable mass postulate, this appears reasonable. For C.C. the quantized QSO redshift and mass results from initial conditions and subsequent interactions, presumably the spatial distribution around the parent galaxy, whereby the higher redshifted QSOs are closest and the lower ones farthest, is the result of the initial energy of the QSO's ejection, its initial size, and various interactions with surrounding material. The more energetic ones travel outward farther and interact more with material, thereby losing more mass and showing lower redshift with distance. Regarding Su's theory, although he predicts at least some of the quantized values, he does not offer a definitive reason for the quantization, as Arp does, which is variable particle mass. Therefore, in my opinion, his theory appears less plausible than Halton Arp's. Continuing with my speculation, I'm going to offer another possible mathematical observation for quantization that could have a yet to be identified physical basis. My simplest equations that reproduce well the quantized decreasing QSO redshifts as a function of uniformly increasing time or distance intervals suggest an exponential decay, or roughly a decay as a function of inverse time or distance. And I'll just go back a bit to that earlier slide for familiarity. I'm referring to the slide here where I showed the mass, the scaled mass relative to the sun's mass, as a function of equal time or distance increments. And the one in purple was the one that showed an exponential dependence, e to the minus 0.6. So what I said is the exponential decay is a fairly common physical phenomenon. For example, it's typical of radioactive decay, but the discrete aspect appears to be unique to QSO redshifts. It's not a continuous decay. It is, again, in a stepwise fashion, at least from what's been observed. An inverse distance dependence, which was also shown on the earlier slide. The inverse distance one is the one in green, where we have distance or time to the minus 1.2, which is basically inverse time or inverse distance dependence. An inverse distance dependence is characteristic of a magnetic or electric field around an infinitely long string of charges, or Curry and carrying wire, and this suggests electric universe theory, where we have intergalactic Birkeland currents pervading the universe. Galaxies formed where these currents flow and could exhibit surrounding magnetic or electric fields with the inverse distance dependence. What is more difficult to ascertain is the quantization aspect. I do make the following mathematical observation that the quantization of both QSO mass and redshift can be represented very well by a sine curve with decreasing amplitude of the same decaying exponential form as my previous equation. And that's shown on this next slide here. This is my own speculation. What I've plotted here is the scale mass, which is scaled mass or the quantized redshift, because they're related, as a function of the time or distance increment. The formula at the bottom, m over m0 equals, the equation on the right is actually an absolute value, and that's shown by the bars. And that indicates absolute value. I have a scaling factor of 2.73 times 10 to the 9th. It's a scaling factor which is corresponding to the quantized masses. I have a shift factor for the sinusoidal variation, minus 0.55, and that enables me to set the peaks at the integer values. Therefore, the peaks for the sine curve come out at integer values of 1 through 5. You'll notice that the peaks occur at scaled masses of 2.05 times 10 to the 9th, etc., for increments 1 through 5. And what I reproduced there is the table earlier where I showed the average scaled mass ratios as a function of the z peaks, the redshift peaks, and the increments. And the arrows there show how well the sinusoidal curve, the peaks correspond to those values. They all align very well with them. In fact, the comparison with the observed values shows agreement to within 10%. Now, I don't know what phenomenon might exhibit a sinusoidal behavior with exponentially decaying amplitude. Could it be some form of harmonic dependence? And I'm only offering this as food for thought. I just thought it was rather, I don't know if it's pure coincidence or what, that I was able to come up with a sinusoidal function that matched the z-peaks, or the mass ratios that result from the z-peaks. The z-peaks are shown in red, decreasing trend. The mass ratios are shown in the dotted curves here. And the predicted values, as shown, the 5 here at the tops of the peaks, align very well with the ratios that were derived from the regression analysis using the much earlier data from C.C. So finally, in summary, my approach to the topic of quantization of intrinsic QSO redshifts, especially based on the lifetime work of Halton Arp, was purely mathematical. Developing a theory for intrinsic quantized QSO redshift is beyond my experience. I postulated a geometric explanation of intrinsic redshift possibly dependent on mass to the 2/3 power related to possible attenuation of light energy and therefore frequency within the emitting nucleus of a QSO, compounded by a further dilution and therefore energy and frequency decrease due to spread over the surface area. To do the quantization aspect justice, I summarized 2 theories by other experts and examined their plausibility within my realm of knowledge. Finally, I offered at least a mathematical representation of the quantization aspect as food for thought. That concludes this presentation.